what I'm going to demonstrate now is how can we improve upon this, and we can actually start looking at multiple linear regression. Okay, so if I go back to my graphs that I plotted, I'll just scroll up. Okay, there is some correlation here. It might not be terribly strong, but these may indeed attribute to the number of the album sales. So if I then go to analyze, back to regression, linear, and this time what I'm going to do is I'm going to put the other variables in. So I've got my advertising budget and my attractiveness of band. I'm going to put them in under an enter, so all the variables will appear in there in one go. I've already got the plots set out, so I don't need to change those. Okay, I'm going to stick with the defaults of 5% level of significance. Don't worry about saving, because we can save all sorts of output from this, but we're not too worried about that on this particular model. Okay, if I then press OK, this will conduct my analyses for me. Okay, and you'll see now that our measure of fit has gone up from around the 36% mark up to a 66.5% mark. Okay, and the adjusted R-square value is now plays an important role. Okay, because the adjusted R-square value also takes into account of the number of variables within the model. Okay, if we look at the ANOVA table again, we've got a significance value because it's less than 0.05, so our p-value suggests that we reject a null hypothesis. In other words, our model is actually predicting something. Okay, scrolling through again, our coefficients now are number of plays on the radio is significant, advertising budget is significant, attractiveness of band is significant. But what we notice this time is that the constant is not significant. Whenever we're modelling within regression techniques, we always keep the constant in until we get to a step where all the variables that are left are significant, except for maybe the constant. If the constant's not significant, you take it out to the last step. So I'm now at a stage where I can actually take it out. So although these plots here are valid, okay, they're not reliable because this constant needs to be taken out of this formulation. So I'll go back to analyze, regression, linear. Okay, and under the options button I will uncheck include constant in equation, then press OK. It gives me some warnings and some notes and so on. It says it can't be depicted in a normal way. Okay, but R square this time is shot right up to 95%, but it says it might not be terribly good at doing that. Okay, but we'll see whether it's not bad by looking at our output. Again, our ANOVA is significant, and now we notice that all our variables are significant too. We needn't worry about these residual statistics. Okay, here's our normal distribution associated with our standardized residuals. The mean is close to 0. Okay, and the standard deviation is close to 1, which is what we want to observe. And indeed, if we look at the probability plots, you see that the plot is very close to the identity line, which is what we want to see too. And also our residual plot shows a random scatter, so there's no obvious pattern there. One thing that we have missed out in this particular set of analyses is, if I go back to my regression on linear, okay, what I want to do is I want to look at the statistics, okay, and I want the collinearity statistics in there, and the Durbin-Watson. Okay, and we're going to look at the output associated with those. These VIF factors in any model that we come to by the principle of parsimony, okay, the VIF factor must be less than 10 in size. So this VIF value should be smaller than 10, and in all three cases it's smaller than 10, and they're all significant, so they behave themselves. Sometimes you might get a value that's bigger than 10, okay, which means take that variable out of the equation. Okay, so you take it out of the regression stage and remodel it. Okay, I'm looking for the Durbin-Watson statistic. The Durbin-Watson statistic here is 1.97, and that is a value. It's not a test as such. Some people refer to it as a test. It's a statistic, and the statistics should be somewhere between 0 and 4. If it's close to 2, okay, as this value is, then the data suggests that the correlation of the errors is 0. If it gets close to 4, then it suggests that there is a strong correlation, negative correlation associated with the errors. Because one of the assumptions that we make with the errors is that they are not dependent upon one another, so there's no correlation associated with them. Okay, so it's just another way of observing it. Okay, you can find out more about the Durbin-Watson statistic by looking in the likes of Andy Field or doing a statistical search under Durbin-Watson. Okay, and you will find that you will get to this point where it says it's between 0 and 4.